This is okay now?
Yeah. Okay. So hi everyone. Welcome to the third lecture of our series Motifs in Algebraic Geometry. This is the third lecture, and this lecture is entitled Sheaf Cohomology. The speaker for today's lecture is Dr. Umesh Dubey from HRI, and he works in algebraic geometry. We don't want to waste much of your time, so without any delay, we'll start right away. Professor, you can just start.
Yeah. First of all, thank you very much for giving me this opportunity. It's very nice to speak here. So, my plan is this is to reach towards sheaf cohomology. So,
just a minute. Can you just turn on your video? You're not visible.
Just a second. Is it okay now?
Yeah.
Okay. Yeah. Thank you. So, should I start sharing screen?
Yeah, you can do that now.
Okay. Yeah. So I hope this is visible to everyone. So my plan is basically to say a few things about sheaf first before we go to sheaf cohomology. So I will start with recalling few facts and few definition. It may be well known, known maybe to all of people here, but I will recall few facts anyway. So please feel free to stop me if you have question, and like any other suggestion, so that I can make that changes in next time. So my plan is at least I will take one more lecture, and it depends how it evolves. So yeah, so my handwriting may not be very good here. Let me just here. So first, let's start with definition. So before we go to the sheaf, we start with the pre-sheaf. So pre-sheaf, everybody knows. So first we start with the topological space X, and here this op X. This you can think of as a category or directed, as a set also, ordered set. So there is ordering is given by the inclusion of open set. So here objects you can think of is like open subsets of X. And the circle here is this opposite category. So what does that mean is that if you write down this condition here saying that functor from this category to this set, so that will give you pre-sheaf of sets. So that's here. So pre-sheaf of set. So this, if you translate this data, is basically saying that for each u, you are given some set which you are calling fu here, and whenever you have an inclusion here, you have similarly this fe here, and there is a restriction map. So there is a reversal here. So this, sorry. Okay. Yeah. So there is a reversal map here. So this either you can say restriction or row, whatever restriction, some convention. And so the functor condition, you can imagine, like if you have, so here, for example, this category, when you are looking at this morphism, only morphism in this category is this whenever there is an inclusion, otherwise there is no morphism. That's so you think of this category here as the only morphism is whenever there is inclusion, unique map. So for example, if u is equal to v, then you have this unique identity map, which is, so it should take this to be identity. So in particular, restriction from u to u is identity. And there is a composite similarly if you have triple inclusion. So so therefore pre-sheaf you can think of as a inductive system also, if you think of it as some kind of inductive set. Or if you think of it as a category, then you can also think of it as like a functor. So that is the pre-sheaf. And if you look at this Tohoku paper, so what he also defines something called diagram of schema, so a diagram of scheme. Uh, so where he takes certain uh, this collection of set and certain relation. So you can think of this will fit in that meaning in that language also. So you can think of that way also. So as a particular case of that set. So you can define this pre-sheaf now various ways. And for because this generalizes many of those example from uh, topology. So therefore, I mean, like element here in FU, this set FU you are calling section. So whenever you say section here, they just mean that it is an element of FU. And another construction which you can do here is that you can define this what is called stop at a point, which is uh, direct limit. So this is running over all the neighborhoods of X. And as you can imagine, there is a map from FVX to this direct limit. So, therefore, I mean, you get this is another set. So for each point, you also define this effect, which is calling as stock. And this is a functorial also. So this by property of this limit, etc., you can see there is, if you have a map from F to G, then there is an induced map from Fx to Gx. So this gives a stock functor also. So there is a stock functor, which will, I mean, you can see from here. So far, I just saying set, but quickly we'll go to some other cases. So you can see here. This is a functor. Again, you can check this. I won't check. So, right. And now another thing which we will use later is this global function. So global function, now you can think of is this notation use gamma X for a pre-sheaf or sheaf later, I mean pre-sheaf. This is nothing but because X is a particular open set sitting there. So you can take value there. So you can just define Fx. So this will be. So I hope this is clear so far. Right. So, okay, I think yeah, I'll have to scroll only. Right. So now, okay. Now, such a data, when do you call it a sheaf? Okay. So sheaf is again. You must have seen. So this is additional to a gluing condition. So whenever you start with some open cover, let's say for some open subset U in X, and you are given a section in this F U alpha, then you want that. So first of all, if so there are two conditions. One condition is that let's say condition A is that if you have S and S prime, let's say S and S prime in Fu, which agree. So sometime also you say that S restricted to U alpha. This just means that restriction applies on this S. Uh, then you want that this S to be sorry, S to be equal to S prime. Okay, and the second condition is the yeah. So this says somehow uniqueness. If, the second, which the gluing part is that if you start with a data that S alpha from Fu alpha, with the condition that for whenever you restrict to U alpha intersection U beta, suppose this agree for all pair S alpha and S beta. Then you demand that then this condition says that there exist. So you can glue this, and there exist S in Fu such that this S restricted to U alpha is nothing but S alpha. Okay, so I hope this is clear. So these two conditions, so the first condition somehow says that this will in fact become unique. So there is a unique section. You can glue this local section and get a unique section. Okay, so now of course this was that object. So these are very special sheaf. So I can again form a category. So this category is the all sheaf, and then morphism, I can take the underlying morphism of pre-sheaf. So here, as I said, the morphism pre-sheaf, if you think of it as a functor, the morphism can be thought of as a natural transformation, which again, you can write down the precise condition for each U and V. There is certain commutative diagram. So here this is, you can say this is the full subcategory. And now the point here, what I'm trying to say is that there is this sheafification functor. So given any pre-sheaf, you can construct what is called a sheaf associated to that. And yeah, can associated sheaf or F++ or either way. So these can easily defined as going to that either you can collect all the stock and put some equivalence relation depending on those two conditions. You can easily define this. The point here I want to make is that this, you can think of it like a left adjoint. So there is some not only you have this construction, there is a map from this sheaf to associated sheaf here, such that whenever you have any sheaf and a map here, so when you think of this is like there is no difference between this. You think of this as same as this. So there should exist unique factoring through this. So whenever you have a map to this sheaf, so this condition here is like saying this sheafification is a left adjoint to this forgetful functor, which if you write it in terms of natural isomorphism, so this is like I mean sheafification. Natural isomorphism between this bifunctors, which are appropriate category you have to see. So so this is very crucial because as you can imagine, if you change this category of set to some other category which has nice structure, it's much easier to prove that pre-sheaf will have those structure. But on the other hand, it may not be easy to prove without this simplification functor. So, and it may not be there. Um, so that maybe we'll observe later. So I will not go into detail of this construction here, but this you can easily find this simplification functor. Okay. But it has this, I mean, universal property, you can say. Okay. Uh, so now there is another way this safe condition which I have written could be written. So for example, let me just go to the next page. Yeah. So as I said here, this so far I have said everything for set, but this whole thing could be set for any category A. So you just imagine that this will be something like a functor from this to A. And this collection here. So now similarly, the gluing condition, you can define like what I stated earlier in A and B. So there should be unique gluing of local sections. Now, if you have, for example, A has a product, etc. So if suppose A is nice, like this category of set, there is another way to say this sheaf condition, which is saying that equalizer exists. So you can write that data in following diagram, which is that. So starting with any cover. So again, the same notation. So U alpha is open cover of this given any U, open in X. You have, there is a canonical restriction, this product of restriction map here going to here. So this is running over alpha, or you can say I. And there are two restriction here, which will go to this pair of alpha and beta. So this condition here, what it says is that, so this diagram here is this Fu is equalizer of this, the later, this double arrow here. So which means that if you see the definition, it is like saying that given such a collection of local section, if they agree here, then you can glue and get a unique. So you can define like this. Later we will see that when we specialize to this additive category, it simplifies even further. So, or even abelian category, then you can write it in terms of some exactness of some sequences. Okay, so again, I leave all detail to fill in here. So what I just mention is that this sequence here is equalizer is equivalent to that condition A and B, which I stated for the sheaf condition. Okay. And now, particular case, as I said, if I take this A this category of abelian groups, or you can take category of any other R module, etc. So you can, so let me just for simplicity, I'll stick to one here, but you can use any such example. Later on, we'll see that you can take category of rings and category of R module, etc. So you'll get various notion. So this, since this will be used, so you'll get a special name here. So this is the pre-sheaf of abelian pre-sheaf or abelian sheaf. So, so this abelian sheaf is nothing but, um, see this pre-sheaf, but the underlying set has this abelian group structure here, and the sheaf conditions are satisfied. So, as I said, in this case, you can write down this sheaf condition as saying that, because the advantage is that if you have a morphism of abelian group, you can add them. That's the point of additive category, add and subtract. So you can simplify this uh, into such a sequence. So this will become, if you may have seen the kernel, I mean, it's like a kernel of this difference map. I won't write this whole map. This is just, you can see those restriction beta difference. So difference of these two map here. So this will, the equalizer here can simplify if in this setup into this. Okay. So let me, so the, so I hope this is clear. So this is the safe condition now. So you can check this condition to get this. Another observation, sometime you see that this data of pre-sheaf or sheaf is given only for the basic open set. You don't have to like describe it for the whole set. And by the sheaf condition, you can glue and extend canonically to whole thing. Yeah. Okay, so some easy example here you can think of, like each open set you can just associate this particular group, or you can think of as a ring, or any ring you could, in place of Z, you could have taken any ring. So same example, same way you can define this Z. And as I said, the restriction is nothing but this identity here, because it's for each. So constant. So you can get this pre-sheaf, and then you can sheafify if. So you can also define like this will give you a constant pre-sheaf. And you can take sheafification to get the constant sheaf. So this just a, I mean, you call it something, then this is like that plus what I said earlier. Okay. And yeah, you can see it's connected, then this may agree, and various property you can work out and then write down this precisely. And you can also try to check what is the sheaf various thing which I defined. So I leave it for you to check to find out what are the stock here. A global section is clear, that is immediate, like it's the same Z here. If it is connected, otherwise yeah, you have to work here. Another thing here, the next example you can see, suppose you start with any other topological space Y, and then you can take for any U, you can send it to this continuous map from this open U, which has that topology from X. So this to Y. And now, okay, as you can imagine, like you can think this is the reason why we are calling this a restriction. So here, if you have a continuous function from V to Y, you can restrict to U and get a continuous map here. So, okay, so this is a one type of function which I have given, but there are several thing. For example, real valued function, complex valued function, or if you have more structure on your X, you get several other type of sheaf on this. For example, if you have a manifold, you can consider in various differentiable function or C infinity function. So all type of function could be defined and could be checked that they have a sheaf property, meaning the gluing hole. So you can get a sheaf of this becomes a sheaf here. Okay. Yeah. Okay. I hope there is no question. Right. So now, yeah, there is another example here, which is useful, is that I start with any point here, X in X, and I can take, I mean, let me just call it F direct sum. I could have done the same thing with product also. I mean, for example, yeah, here I'm taking abelian group. This is a nice category. It has all the uh, product and co-product and this direct sum. So I don't have to worry. So this will be again abelian group. Um, so you can check that this association here. So this one, so this you define first. So always you define pre-sheaf, that because that's easier. Uh, so they just associating this particular abelian group, and now as I said, okay, and let me follow my notation. So you can see there is obvious restriction map here. So what you do is just restrict to that particular component. Okay, so similarly here. So you can define the restriction here, and so whatever element here, you just take only those components which are for which X lies in V, because here U is included in V. So you take those projection onto this vector. Yeah. So this will be pre-sheaf, and like it's you can check that this in general is not a sheaf. I mean, uh, this one is not a sheaf. So because that gluing data, for example, I mean, if for example, if I would have taken discrete topological space where each X is open, and you can just imagine that the gluing condition says that for this should become product over this whole thing, because each mx should give rise to by gluing some section, but it's a discrete, so somehow there is no condition. So you check. So I leave it for you to check that by taking some X discrete uh, topological space non-empty with at least few points. So you will get a example where this won't be a sheaf. And yeah, on the other hand, this one you can check is will be sheaf. Yeah, I hope this is clear. So I will leave it all this checking for you. Uh, okay, let me just mention one more example since we are doing this algebraic geometry. So this very special, very just from simplification point of view, I just wrote here the affine case, but there are, I mean, you can in general consider any scheme or any more general algebraic spaces. So those you can define this very special this sheaf of ring. Um, so which is that if you think of this DF is nothing but these are the principal open set. If you know, so this is like spec of RF. Also, you can think of. So this DF is form a basis for the Zariski topology. So as I mentioned earlier, so if I just describe some sheaf on some basic open set, it will canonically define the sheaf, meaning you can define it for any U because you can just take a any open and this cover by this EF and then you can glue and get value for any U. So this RF here is the localization at F. So you can invert this an element F in this R. Yeah. So this will sometime equally structure sheaf associated to this. Yeah, so these are some example of sheaf and pre-sheaf. I hope gives some idea. Now, of course, there are certain things. So there are more general, lots of other example, but I have not mentioned here. For example, if you have a sheaf of ring, you can take a sheaf of module or that sheaf of ring. So again, we use the same notation for any other sheaf of ring. And this is a sheaf of module. So meaning there is a abelian sheaf with some for each U, this FU should have OXU module structure. Again, this thing you can define. So now the thing is, if you see the Tohoku paper, for example, as I mentioned earlier, that pre-sheaf can be realized as this category can be realized as that what he calls scheme, something diagram of scheme in that particular category. So it can be thought of as like the diagram of scheme in this category of abelian group with the diagram that set or the data, if you in his notation, so he calls this I, and then there is this arrow. So vertices are this open set, and these arrows are nothing but those inclusion. Yeah, let me not write it. So you can see that this can be identified with that. So for that, in general, what he has said is that if your category, so first thing you can notice that this category of abelian group, this has all the nice property, or more generally R module category. These are the category you may have seen that they are example of category satisfying all those various axiom of this Tohoku paper in that he had said, for example, AB1, AB2, which gives that abelian category structure. And there are this 3 and 3 star, which gives that there exist infinite direct sum and direct product. So AB3, let me just recall. So this is uh, existence of this infinite direct sum, and 3 star is the existence of infinite product. So there is some dual axiom he has stated. So this proposition says that whenever your underlying category has all those property, you can prove that same thing will hold for that diagram category in particular, I mean, applied to this case. So you will get, you can prove that that holds for this pre-sheaf. And it's not very difficult to check also. Here the thing is that you can do all the construction. For example, if you want to define kernel of any morphism of pre-sheaf, let's say if you have a map from F to G, then you just what you have to do is just define pointwise. So on U is just, you have to take kernel of, there is an induced map Fu from F of U to Gu. So these are abelian groups, or in general, it could have been any abelian category. So this will exist as a pre-sheaf. And this is another, of course, exercise to say that this in fact is a sheaf. So this will again exist in the category of sheaf. And the point what need a sheafification is this co-kernel part. So in that co-kernel, what you have to, you can define this co-kernel for Fu, but then you have to sheafify. Um, I mean, this kind of data, and then you do the sheafification. Let me not write in detail. So basically, so there are examples where in general, the quotient may not be, quotient of sheaf may not be sheaf. So that obstruct from these two existence of this co-kernel. But what we have here is that you can take a simplification and prove that this has this required property of co-kernel. So it will have that universal property that whenever composite something is 0, then it factors through this. So that property you can imagine is like so again you can see that you have a map like this, and whenever something is is composing with this becomes 0, then it will factor to this. So this property, as you can see, that this is the H is a sheaf, and then this should is a sheafification, so it should factor through this. So some of this kind of checking you have to do to say that this it will be an abelian category. So you can check that. So first part is easy for a pre-sheaf, and that for a sheaf part, you have to do this modification. And then, of course, it's a checking that the AB2, which says that, I mean, kernel of co-kernel and co-kernel of kernel, these are isomorphic. So there is a canonical map, induced map, so that should be an isomorphism. Okay, leave it to that. Yeah. So from here also, it is clear that when you define co-kernel in pre-sheaf, in general, it may not agree with the co-kernel for a sheaf. So and kernel is already a sheaf. So this justifies this fact that, I mean, that two construction of this kernel when you do in pre-sheaf or this sheaf, they agree, but for the co-kernel it doesn't. So in general, it is not an X. Okay, here exact means that, yeah, it should in particular preserve this kernel co-kernel. Right. So okay, so yeah, I'll not go into proof of this. So this not very difficult, but requires some calculation. So this could be proved here in the case of sheaf. For pre-sheaf, it will follow. Not right. Now, uh, because of this, some result proved in this paper, Tohoku paper. Now people call it the category which satisfies this axiom AB5 and has a generator to be. Sometimes people ignore this, but these two condition if are satisfied, then they call it a growth indica abelian category. So some category which satisfy AB1, AB2, you already call it a abelian category. Further, if they have this, there are some list of axiom which he has stated. So one of them which I stated here is this AB3, which says that existence of direct sum. Then there is this AB4, which which involve existence of direct sum, but also says that direct sum of monomorphism should remain monomorphism. And finally, there is this AB5, which is defined in terms of inf and sup, like certain sub-object for. So this is stated something like this. Um, okay, where these are defined appropriately. It could be equivalently stated some filtered limit, co-limit, exactness of that. So these axiom become equivalent to some more condition. So the point is that here this abelian group already has all these properties. So this, as I said, abelian group, this has this AB5, etc., and it has a generator which is that Z itself. So Z is a generator in general for any ring. The same ring becomes a generator because he has proved. If you see this Tohoku paper, so he proves that in an additive category with a direct sum, etc. In fact, any family of generator, you can make it a single here by taking direct sum. And the other fact is that this being a generator become equivalent to saying there is some uh, like copies of Z several, infinite times. See, this should get any object is a quotient of this. So, yeah. So from here, you can see this Z become generator if you have an abelian group. So AB is easy to see that this has all these properties. So now that again, that proposition 1.6.1, which says that whenever your underlying category has this type of property, then you can push it for the pre-sheaf. And then you need some more argument for the sheaf part. Like you have to then analyze the sheafification. How does it behave? And then using that, you can deduce for this sheaf part. And the generator part, again, using this generator of AB, you can cook up something called this constant, which you can define a generator for this pre-sheaf also. So which is that on U part, it takes the value this generator Z, and rest of that it just 0. So if you so this pre-sheaf here you can see is the generator. For sheaf part, you have to define appropriate sheaf version here. So and yeah, we can get a generator. Okay. So yeah, any questions so far? Yeah, we'll come back to this maybe later when we see more properties. So therefore, what I said is using some of this property, uh, more general construction, you can get this thing. And what he proved is that in general, if you have some category with this, what we call Grothendieck abelian category, it has enough injective object. So we are heading towards that possibly. So before that, let me just mention, as I said, I can take a sheaf of ring. So this OX denotes sheaf of ring, or sometimes called ring spaces. So it's a topological space with the OX is a sheaf of rings. OX, all OX U are ring, and then restriction is a ring homomorphism. And all such data, you can define this category mod OX. So which is that each FU has OXU module structure. So it's a sheaf of abelian group.
Professor, there is a question. He's asking you to explain the term generator of a category.
Oh, okay. Yeah. Okay. Okay. So generator here. So first of all, let's define family of generator. So these are some collection of objects. It says that for any object A, and you take any sub-object which is different from A, B is not equal to A. So if you see the definition, so what it says is that there should exist, let me say too many times alpha. So there exists I such that there is a map to this which does not factor through this. This map doesn't, there does not exist any map from UI to V such that this factors through this. So basically, like any such sub objects, sorry. Let me say like this. Okay, so now B some notation. So this B is a sub object here, and this canonical inclusion. So what generator means? So this is the family of generator. Some indexing, sorry. So you call such a collection in this category. For example, think of AB. So these are, so we should have a property that for any sub-object here, there should exist a map such that it doesn't factor through this. So that's a definition. And what the result which I mentioned, what he proves is that this property become equivalent to saying there is this uh, quotient here. Yeah, so that does not exist. Okay. So there are other ways to think of this, like as he mentioned in the paper, like um, certain consequences like this sub-object form a set, etc. Uh, but this is the definition, and yes, is it clear? There no question.
Yeah, he says it's clear.
Okay. Yeah. So let me go ahead. Yeah, this is, as I said, this I am following that Tohoku paper. So this is from there. This result which I mentioned. Right. So as I was saying that now if you have a range spaces, you can another category which you can form is this uh, sheaf of module. What do you call this category of sheaf of modules? So this category here is what we are interested in, and the way we proved here for abelian sheaf, etc. You can okay here. I didn't mention. So you can define direct sum and direct product. So as I said, this AB3, to prove AB3, you need to prove that this has a arbitrary direct sum, and for AB3 star, you need to prove it has an arbitrary product. So what, like as I mentioned, like pre-sheaf level, it's easy to define. It just you associate a pre-sheaf because underlying category has those structures, so you will get that. But in general, they may not be sheaf. One of them is, but not the other one, as I think we found in that example also. So therefore, you have to sheafify. So using the help of sheafification, what you can prove is that even this category of sheaf will have AB3 and AB3 star. And of course, you need to do some work to prove other property, but let me skip that part. So what I'm saying now is that if you take now sheaf of module, so here also you can like you can go pointwise and define all that uh, direct sum and product, and you will see that like you will have OXU module structure on that direct sum, and it has all that universal property um, of that product and co-product. So you see that there is this okay, I'm not taking here pre-sheaf, but this is the my sheaf of module. So you can do the similar construction, and you can get that this is the this has AB3 and AB3 star. And furthermore, I mean, of course, you have to. So here we are using the fact that OXU, this is a ring, and this is, of course, there is some convention. You have to fix some left module. I have not mentioned here, but always, yeah, there is. If you have to fix some left or right, it's commutative. It doesn't matter, but otherwise you have to be careful. Sheaf of left R module. So that category will again, sorry, there is some more question. Okay.
No, there are none.
Some remark. Okay. Yeah. Uh, so So this sheaf of module here again, so this category here mod OX will again has this kind of property that it will satisfy AB3 star, and this um, direct sum of monomorphism is monomorphism, and that filter limit exactness. So those property you can same way prove for this category also. So because those properties are already there for this R mod. So you can see that this will also, there is another way of proving this thing here is that all of this R module, any sheaf of R module has the underlying sheaf of abelian group. So you can forget the R module structure and you can go to that abelian group, sheaf of abelian group. And many of those properties you can check there, and then that will hold here, something like that, like 4 and 5. For 3 and 3 star, as you can see, like you have to do that pointwise construction and then do the simplification to get that OXU module structure, and then you prove that there is OXU module structure on that. Yeah. Of course, here I have taken OXU as a sheaf of ring. Yeah, I'm not taking pre-sheaf of ring or something, but these are sheaf of ring, and you can define all these structures. So whenever we are saying mod OX we are considering is sheaf of ring. Okay, again, yeah. So this is a fact here, so which you can prove. Okay, now so we need to come back to that some more example. So yeah. So other thing what we need is that now we want to go to that. So I hope you have seen the definition of injective object and projective object. What we need here is injective object. So this is the categorical definition which you can imitate here in this category of sheaf. So now we have got this category, so mod OX. So many times we will specialize to this category ABX, but many of those results are there for mod OX as well. So we'll now work with this example, and we want to basically show that there is enough injective, meaning any object you can write down the injective resolution, and once you have an injective resolution, so there is the global section functor. So I have defined this global section functor. Okay, so what is the plan? So plan is to basically take this functor here. More generally, you could have taken here this to be mod OX, and this will go in the module over this particular ring, right? Because everything has this kind of structure. So what you're doing is that take F and just send it to, as I said. Right? So this is a functor which I have mentioned earlier. So now you want to define the right derived functor for this, and this ith cohomology, I mean, Ri gamma will is what will give you the sheaf cohomology. So, so basically, the way you define this is you just take the injective resolution and then apply this gamma on that and then take the cohomology so of that complex. And it was another, so there we used the fact there was more general result, maybe we'll try to recall those, that something becomes universal delta functor. So some property called universal delta functor. So whenever there is enough injective object, so this, the way we are defining this functor, they become universal delta functor, therefore they agree with this right derived functor. So this uh, once your category, abelian category, has enough injective object, you can immediately define your right derived functor by simply by taking the resolution. Um, so So now the aim is basically to, in this category of which is nice Grothendieck abelian category, there is a functorial injective resolution you can write down for every sheaf, which we are denoting by I dot. Uh, and following the idea of Godama. So this Godama resolution you can take and then take could, I mean, you can define so some nice resolution and you apply this functor, you get the derived right derived functor, and which is what you call it the sheaf cohomology. And if you are in general mod OX category, then you can get similar resolution you get there, and therefore you can define this more generally, such a cohomology functors. So you are getting the cohomology functors for each I. This is for this reason sometimes this is also written as H naught X dash this functor. So this, because this uh, the way if you see the construction, this R0 will agree with gamma whenever you have a left exact functor. So again, of course, you need to prove this is left exact. So which is amounts to saying like if you have a short exact sequence like this, and you apply gamma functor on that, and this is where you can see that sheaf property is being used. You get this is exact. Sorry, this is a bit. Yeah, this becomes exact. Okay, so it's not very difficult to prove. Maybe if somebody want, we can come back to this. Otherwise, so once you have left exact, so then the derived functor, all this using this resolution you define, and that R0 agrees with the gamma, and this following this notation. So this is same as this. Uh, yeah, so let me just see if Yeah, so we have to now study the injective sheaf. So which are the injective object in this category billion X? But as I said, you could have worked with mod OX also, and injective objects are defined. So I don't know if I said here, but yeah, I was trying to say that. So injective object was defined where so some object says that so some sheaf, abelian sheaf or OX module sheaf says that this functor is exact. Of course, so you call it this is injective sheaf if and only if this functor this functor here is exact functor, and which you again from the fact that this is a left exact functor, only thing need to check is the right exactness, which amounts to saying something like uh, if you have an inclusion and and any map like this, there exists an extension. You may have seen in the ring case. So similar thing, this is very categorical. So if such a property holds, then you call it I is injective sheaf here. Yeah, so everything happening in the sheaf category. And so the point here is that injective sheaf, there are enough injective sheaf, meaning that if you take any sheaf, I can get a monomorphism to some injective sheaf. And moreover, what we can see is that in fact this is functorial. I mean, there is some functor which associate this F to this. So uh, yeah, that's what is the aim. And once we have done this, so as I said, once you achieve this in this category of sheaf, you immediately get the definition of that sheaf cohomology. Okay, so maybe what I can do is that I can stop here and come back to that existence of resolution and uh, some variant of this functor gamma possibly next time, and then something like gamma phi what he has defined for some collection of closed subset. And yeah, then maybe I can start with from here from next time, if that is okay. Okay, maybe I can stop here.
Okay, great. Thanks for this wonderful lecture, Professor. Um, so
Are there?
today's session ends here.
Okay.
We'll see you next week, Saturday, 11 a.m. at the same place. Um, yeah, so goodbye, everyone.
Stop share.